Everyone, and welcome to this module on Introduction to Continuum Mechanics. This is going to be a very short video as I'm not going into deriving all the equations, but just give you a very brief introduction on a new concept that I call intermediate configuration. However, the book used current configuration as a reference configuration, which I find somehow unsuitable for a person who's in the introductory level to continuum mechanics. So I use the reference intermediate and current configuration for the title of this module. So you've been already introduced to reference and current configuration, but let's see what this intermediate concept is. All right, so for the motivation, let's suppose that you have a pipe, you have a river, or you have a control volume where you have a fluid inside this. And if you remember, at reference configuration, we were at time t0, and we also had this current configuration time t. So suppose that I change this t to tau to time tau. So this is time. Let's say that this is t equal to tau, and here t is equal to t0, and here your arbitrary time, let's say t, small t. So you arrive here, so you have no idea about the reference as well as the current configuration. So you arrive here at a time t, and you want to measure a parameter here. So you have no idea about the reference and current configuration. You arrive at an intermediate configuration. So suppose here in our famous illustration here, we have our current and reference configuration. Here is our reference and our current configuration. So you already know that if you have a point here, let's say P0 at time T0, P, let's say, and then this, let's call it P, simply P. Okay, this P in the current configuration is P at, here we call this tau, for example. We already called it T, for example. And we already said that if this is our displacement vector, so we call this capital X, and this is an element vector, and here we had this displacement, this element vector in the reference configuration. We called it X, and we basically called this one the displacement vector. So we called it U, and we already said that U is equal to, so X plus U is equal to X, small x, so X, small x minus capital X. We said that this is basically the displacement vector, U. So, but if we come to this, this illustration here, we have another configuration here, like this one, that we define as, that I name basically as intermediate configuration. So basically, you have an intermediate configuration here where you have your point P at time t, and now you change this P to time tau, as we have in here. So you have P at time t, you have P at time tau, and you have your P at time t0. And you, for example, come here, you use this intermediate configuration basically as your reference configuration, and then you continue from this point to here. So you continue from here to here. Initially, we basically moved from here to here, but now with this intermediate configuration, which is here right now, we basically are going to put this intermediate configuration as our reference configuration, and we continue from here to here. This is basically quite frequent in fluid mechanics. However, we have this concept in, let's say, solid mechanics. So, for example, for large deformations, for example, we have, this intermediate, we can define an intermediate configuration. So where we have, for example, measuring the displacements or some parameters, and we work from here to here. So we completely forget this reference configuration. So we may use it at first, but later we try to adapt. We try to, for example, converge our solution from intermediate configuration to current configuration. So so previously, if we had our current configuration and we had a reference configuration, so if I draw something like this, so previously we had our reference configuration and current configuration. So in the reference configuration, oh, I shouldn't have put this in here. So let's delete this one. So we had our xi, small xi, was a function of capital Xj and T with the reference configuration. It was xi, capital Xi, small xi, which was a function of xj and t, t0. But now, using the intermediate configuration, so this was when we had, let's say, current and reference configuration together, but here we have current and intermediate configuration together. So let me put this in here. Let's extend this bit. So here with the current and intermediate, let's say that we use prime in here for the intermediate. So I have let's use prime for the current configuration. So I'm not going to write xi again here. So I'm going to write x prime I is equal to x prime I x. So now here we have the intermediate configuration here. So I'm going to write here x at the time tau. So I have p tau. So you see here that I have x prime is equal to x prime I, x, and tau with, this is the reference configuration. Now it changes to intermediate configuration. So or intermediate configuration. Now we have the intermediate configuration. So this becomes xi because this is our intermediate configuration. Then we have x prime I, which is a function of xj, and now we have time t. So it is like, if I show this with another color like this purple in here, so x prime, now if you have this pt, then this becomes your intermediate configuration. It becomes your reference configuration. So then you will have this as x, and this basically changes to x prime. And now you have your new u in here, defined as x prime minus x in here. So I put a legend here. So we have the current intermediate. And if we have the blue one, it is basically the current reference configuration here. So what is important is that you can define this intermediate configuration as the reference configuration. So it is not necessarily true that in all the possible scenarios, you know the reference configuration. You might know it, you might not know it. So if you know it, so you use it. If you don't know it, you can use an intermediate configuration. You can select an intermediate configuration at whatever time you want. So it is not basically T0 again. So it is T, and you continue with this intermediate configuration to find the current configuration. This is quite, common in fluid mechanics. However, we know we can use this in solid mechanics, because in solid mechanics, most of the time, you know the reference configuration. So, for example, you know your beam is, for example, at rest, for example, or your beam is basically pre-stressed, and you're going to apply another load, for example, a moment to this, and you're going, so let's say that you have your beam at rest, so you know the reference, and you apply a load, so this becomes your current configuration. But later, you for example are going to apply another moment to this, so this current configuration becomes your intermediate configuration. For example, you can think of it like this, and you have, let's say, this pre-stressed beam. This becomes your reference configuration, this intermediate, and you apply a moment to this, for example, and this becomes, for example, this one. This becomes your current configuration. You can think of it like this. So basically, based on this, you can define different, different concepts. So, for example, if we have the current reference configuration, we can have the current intermediate configuration, where, for example, here we defined V at at the current configuration and at time t. So it was the partial derivative of x with respect to t. But here we use v. So here our current configuration is changed to prime. So we use x prime, as book also used. And we have, instead of t, we have tau, which is equal to partial derivative of x prime with respect to, now t is tau, because here we are at time t equal to tau. So, for example, here we had f, the deformation gradient, as del x, was the partial derivative of x with respect to capital X. But here we have f equal to del x. Now, this x is x prime because we are in the current configuration. I put a prime in here. This one is equal to partial derivative of x prime with respect to small x, because this x is now our intermediate configuration. So maybe here x, capital X, here x, and x prime, maybe this x prime. And the book actually put this t in here to distinguish that this is a current intermediate kind of, tensor. Or, for example, C was equal to F transpose F. And here we have CT is equal to FT transpose FT. Or B, for example, is here FF transpose. Here BT is FT FT transpose. There's one more thing that I want to mention here, that these are all the tools that we developed so far for characterizing the deformation and the strain in a continuum. So it is quite important to know that you can use whatever you can use, or you can pick whatever of these tensors you want, and you develop your theories, or you use them while you solve a problem. So it doesn't mean that if you, for example, select F, so F, just by picking F, you can solve a problem. So it's not important which one you select, but it depends on how comfortable you are with your solution. You can select C and you solve a problem. You can either select B. You might face some problems, but you finally get the solution. So it doesn't mean that B can't solve a problem, tensor B can solve a problem, or C can't solve a problem, or F can't solve a problem. So it depends on how comfortable you are with either of these, tensors in solving a problem. So pick whatever you want and solve your problem.